Yeah, so far we completed about magnetism and some topic we completed. Today I'll explain about magnetism, terms related to the magnet we learn today. Okay, so let's start the session. So first thing is terms related to terms, terms related to magnetism. Terms related to magnetism. In that, very first one is pole strength. Pole strength. Very first one is pole strength. What is mean by pole strength? So here, pole strength is nothing but it is denoted with letter M. The pole strength is denoted with the letter M. And what is the meaning of the pole strength? It is a property of the magnet to how much effectively it is attracting to the isolated north pole, isolated south pole, that is represent the pole strength. So finally, what we can say about pole strength? Pole strength is a property of a magnet, how much effectively it is attracting to the magnetic materials is known as a pole strength. So I can write here, pole strength is a property of a magnet. It is a property of magnet. It is a property of magnet. How much effectively how much effectively is attracting or repelling the magnetic material is known as pole strength. Is known as pole strength. Pole strength, and it is denoted with letter denoted with a small m, denoted with the letter small m. And next, units for pole strength. Units for pole strength. Units for pole strength is ampere meter. Units for pole strength is ampere meter, and it is a scalar quantity. Understand? It is a scalar quantity. So this is all about what? Pole strength. So what is mean by pole strength? The property of a magnet attracting the magnetic material, how much effectively is represented with the pole strength, and units for pole strength is ampere meter, and it is a scalar quantity denoted with the letter small m. And next term is geometric length of the bar magnet. Next one is geometric length. Geometric length. Geometric length of bar magnet. Geometric length, simply you can write geometric length. So what is this geometric length? Geometric length is a length. Geometric length. Geometric length is the length is the length, geometric length is the length between the ends of the bar magnet, between the ends of the bar magnet. Geometric length is the length between the ends of the bar magnet or edges, physical edges of the bar magnet. So I'll show with the diagram. Let us assume that this is a bar magnet. This is a bar magnet. When this is a bar magnet, this is north pole, this is a south pole, and from this length to this length, from this point to this point is known as geometric length of the bar magnet. Geometric length of the bar magnet. Next, magnetic pole. Next one is what? Magnetic pole. Magnetic pole. What is this magnetic pole? Magnetic pole is a point just inside the edges of the bar magnet, just inside the edges of the bar magnet, and it has the poles have ability to attract the magnetic materials, to attract the magnetic materials. So this is what magnetic pole. I can show with a diagram also. So let us take if I take this is a bar magnet, and this point represent the poles. Okay, this dotted represent the poles of the bar magnet. Understand? So this is how the terminology. Next terminology is magnetic axis. Write down magnetic axis. What is this magnetic axis? Write down magnetic axis. Magnetic axis is a imaginary line. Magnetic axis is a imaginary line. Imaginary line. Magnetic axis is a imaginary line which is passing through the poles of the bar magnet. Now I'll show with a diagram. The diagram is, now if I take this is a bar magnet, this is north pole, this is one pole, and this line is representing magnetic axis. This line representing that magnetic axis. Next one. Next one. Next one. Equatorial line. Next one is equatorial line. Equatorial line. Equatorial line. So equatorial line also imaginary line. Equatorial line is also an imaginary line. An imaginary line. Equatorial line is also imaginary line which is passing perpendicular to magnetic axis at a midpoint of the magnet. At midpoint of the magnet. This is called a equatorial line. So if I show with a diagram, so if this is a bar, if this is a bar magnet, this is a north pole, this is south pole, and this line is a magnetic axis, and this line representing that equatorial line. This line is representing that equatorial line. This is what magnetic axis and equatorial line. Next, magnetic length. Next one is magnetic length. Magnetic length. So this is a magnetic length. What does it mean by magnetic length? So here magnetic length is a length between the poles of the bar magnet is known as magnetic length. Is known as magnetic length, represented with letter 2L. Represented with 2L. Now, if I show with a diagram, so let us take this is a bar magnet. When this is a bar magnet, this is a pole, and this is a pole. From this here to this position, this distance is known as a magnetic length. Understand? This distance is known as a geometric length, and this from here to here, the distance is known as a magnetic length. Understand? The relation between, write down, the relation between magnetic length and geometric length. The relation between magnetic length and geometric length are so this is a magnetic length, and this is the geometric length. So what is the relation? Every time magnetic length is equal to 5 by 6 times of geometric length. So that is, in a mathematically, 2L is equal to 5 by 6 times of capital L. So this is your relation between geometric length and magnetic length. Better take note. So this is what the terminology related to magnetic materials. Next thing is, after having this, magnet with no poles. Magnet with no poles. Yeah, so magnet with no poles, it is possibility is there. So what is that magnet with no poles? So generally, if you take any, actually this is a ring. The ring wounded with wire. Actually, that is called toroid. And next, the wire is constructed as a helical structure. It is called solenoid. And this toroid and this solenoid, when we send the electricity, when you pass the electricity, these two will produce magnetic field. But when this produces magnetic field, which means that this toroid and the solenoid is act like a magnet. But this toroid, this very long length solenoid never have the poles, because these are not, this is not forming the poles. Okay, that is the reason we can say that magnet will be present with no poles. So these are the best example for what? Magnet with no poles. These two will work only when send the electricity, pass the electricity, then only it will show that magnetic effect. Otherwise, this toroid and solenoid will not exhibit magnetic property when we pass current through this instruments. Understand? So these two we can say that magnet with no poles. Understand? Here, so a short solenoid will exhibit poles, but if it is very long, we cannot have the poles for this solenoid. Understand? So this is all about what? Some materials related. Some terms related to magnetic material. Next thing is write down magnetic moment. Next thing is what? Magnetic moment. So better write down magnetic moment. Magnetic moment. How can you define this magnetic moment? Magnetic moment is the product of magnetic moment, generally represented with capital M. Magnetic moment, magnetic moment is the product of magnetic moment is a product of pole strength and magnetic length. Magnetic moment, how can you define the magnetic moment? Magnetic moment is a product of pole strength and magnetic length is represented with is defined as a magnetic moment. So generally magnetic moment represented with the capital M. That M is equal to product of pole strength. Pole strength is represented with product of pole strength represented with small m, and magnetic length represented with 2L. So finally M into 2L represent the magnetic moment. See, magnetic moment is a vector quantity. Is a vector quantity. Magnetic moment is a vector quantity, and its direction is direction always south pole to north pole. Its direction always from where to where? South pole to north pole. And units for magnetic moment is magnetic moment is units for magnetic moment is ampere meter square. Ampere meter square is the unit for magnetic moment. So this is some important information related to magnetic moment. Understand? And the next thing, changes of magnetic moment by cutting the bar magnet. So better write down changes in magnetic moment changes in magnetic moment by cutting the bar magnet. Cutting the magnet. Okay, changes in magnetic moment by cutting the magnet. So first thing is case 1. What is the case 1? Case 1. Cutting the bar magnet parallel to magnetic axis. Cutting the bar magnet parallel to the magnetic axis. Let me take this is a bar magnet. This is a bar magnet. When this is a bar magnet, now if you cut this bar magnet, you know this is a magnetic axis. This is a magnetic axis, and now you are cutting the bar magnet this way. This way you are cutting the bar magnet. So when you are cutting the bar magnet this way, what going to be happen? It's magnetic moment. When you cut the bar magnet, its pole strength, if you cut n number, if you cut this bar magnet as a n pieces, when cut the bar magnet as a n pieces, its pole strength will become each piece pole strength become how much? M by n times. So when cut n parts, then each piece pole strength will be pole strength of each piece is become m by n. Initially its pole strength is small m. When it is a purely the bar magnet, its pole strength is small m, and when it cut into n pieces, each piece pole strength become m by n. When each piece pole strength become n by n, and each piece dipole moment is magnetic moment or dipole moment is magnetic moment of each piece is magnetic moment of each piece is how can you find? Capital M is equal to small m become m by n, so and small m become m by n, and its length of the magnetic will be length will be 2L only, since m, let me take this is m dash is what? M by n, which means that each piece magnetic pole will be reduces how many times? 1 by n times. So this way the changes will occur when we cut the bar magnet parallel to the principal parallel to the magnetic axis. And same way, one more thing, when we cut case 2, that is case 2, so write down the case 2. Case 2 is cutting the bar magnet perpendicular to the magnetic axis, perpendicular to the magnetic axis, cutting the bar magnet perpendicular to the magnetic axis. The thing is, again let us take this is a bar magnet. When this is a bar magnet, this is the poles of the bar magnet, and here to here this is the length of the bar magnet, and this is a geometric length of the bar magnet, and this is your magnetic axis. When this is a magnetic axis, if you cut the bar magnet this way, n pieces if you cut, and here pole strength of the bar magnet is m. When the pole strength of the bar magnet is n, and you cutted this piece bar magnet as a n pieces, then each piece pole strength will be how much? See, the each piece of magnet pole strength remains the same, which means that that is m only, small m only, it will not change. When the pole strength will change? When the pole strength is cutted, when the bar magnet is cutted parallel to the principal axis, then at the time only pole strength will changes. Remaining all the cases pole strength will not change. Understand? So when you cut this bar magnet perpendicular to the magnetic axis, pole strength will not change. So it remains same, that is m. In that case, when pole strength is not changes, but what going to be changed here? What going to be changed? Length of the bar magnet will changes. Understand? Length of the bar magnet will change. What is the length of the bar magnet? Length of the bar magnet is length of the bar magnet become 2L by n. When the length of the bar magnet is 2L by n, then magnetic moment m dash is equal to m pole strength into length of the bar magnet is m by n. Since m dash is equal to again m by small n. So this is the way when we cut the magnet vertically, horizontally, the each piece pole strength become, each piece magnetic dipole momentum is same. It will not change. Okay, this is about changes happen in the magnetic dipole. Next, changes happen when we bend the bar magnet. Changes in magnetic moment. Changes in magnetic moment when it's bent. When it bends the bar magnet. For example, initially when the bar magnet is straight, this is away. When this is away, this is the poles of the bar magnet, and this is a 2L, and pole strength is M. In that case, magnetic moment is M is equal to small m into 2L. So this is your magnetic moment. So same bar magnet now, if you stretch into bend into the form of shape of the semicircle. Same bar magnet, when we stretch half of the semicircle, then it is bent. Then what is the magnetic dipole? So you know magnetic dipole means capital M is equal to magnetic moment is equal to pole strength into magnetic length. Generally, magnetic length is nothing but the distance between the poles of the bar magnet. So here the distance between poles of the bar magnet is this now. Since this distance is nothing but actually 2r, that is nothing but diameter. So here the distance is 2r. When the diameter is 2r, but what is r here? How can you know the r value? So already you know 2L is equal to we made into as a half of the semicircle. Half of the semicircle value is pi r. Then r is equal to 2L by pi. You can apply here m dash. This is m dash. M dash is equal to m into 2 into what is r here? R is 2L by pi. So finally M2L is nothing but actual magnetic momentum of the system. M dash is equal to 2m by pi is your magnetic dipole for the given situation. Understand? So this is how the changes happened for the magnetic dipole for the situation.